My talk is half as good as that. So thank you all for coming here today, and thank you all for some of you flew, some of you took time off work. I really appreciate it. The title of my talk is Computational Methods for Advancing a Decarbonized, Equitable, and Resilient Energy Transition. Let me take us back a little bit in history to the 19th century. That was a key time in human civilization because we finally found something called oil or fossil fuels, crude oil, that we can use to power our homes, we can use to do lots of things that we've never done before. Around that same time were key inventions. First is the combustion engine, which many of us are familiar with, which are in most of our cars. Another invention happened at a similar time was the motor vehicle. So you can see how these inventions kind of fit into each other. And then finally, arguably the most important invention of all, the AC electricity, which powers our lives today, essentially defines fundamental human civilization. However, this came at a cost. If you look at the trajectory for CO2 over time, you can see that it's rising. And then if you look at the temperatures as well, you can see that the earth is warming. And some of you might say, I never liked winter anyway, I like it hot. However, maybe I can paint this picture in your mind. These are pictures of real climate events from different news articles. One, you can see the Bangladesh flood that happened in 2021, displaced about 13,000 refugees, killing about 16 people. In New Mexico, 2022, they had the largest wildfire ever recorded. In fact, I was in my cousin's graduation in Atlanta that weekend when I was hearing the news, and I was watching CNN, and 5 times news article came up about extreme events. I've never seen that before. If you look at what happened in South Africa in 2017, the fire killed about 6 people and kind of consumed the whole community. And in California, we have something called wildfire season. It's like every single year from about May to October, we expect wildfires to happen. In fact, in 2020 and 2021, about 7 million acres of land were burned in fire. And in 2022, over $3 billion was spent to reduce the damage of fire. And so if we think about climate change, we think about energy because they are quite coupled. If you look at the fraction of our activities that contribute to climate change, you see that energy takes a huge fraction, a whopping 72%. Now, if you zoom in into the part of energy that takes most of that, it's electricity and heat, and also transportation. And you'll see how these systems are going to start being coupled when you think about the future electricity grid. Now, let's talk about the grid. The grid has a few components. One is generation. This is where most of the emissions happen. So you take fossil fuels like diesel, coal, and you burn them, you produce huge heat. Then you move these working fluids to turn the turbine to produce electricity. And so you transmit those electricity through long transmission lines at high voltages. And eventually you serve some customers, the industrial customers which consume high voltage electricity. And finally it goes to the distribution grid where you and I connect. That's where we plug in our phones, some of our EVs at home. And largely this grid has not changed for centuries. So it's quite been the same, where you have a centralized generation, then you take all the energy to the distribution grid. However, due to climate change, this is changing very rapidly. We need to decarbonize. We're in a fight for our lives. And so you can see that now there's much more things happening in the grid. For example, the homes have solar. You have electric vehicles plugging in as well. You have industrial customers buying batteries, and you also have variable generation. And so how do we coordinate all these things? This is an exciting time to be alive. Why? Because we're meeting at a confluence of different things happening. There's more data. We've had more data than ever before. And so we're able to see the world much better. Secondly, there's also more compute. So which means that the amount of money you spend on computation is cheaper. And this means that we can make much more intelligent decisions. This brings me to my PhD journey. It composes of 3 parts. One is on weather and looking at how weather can impact power systems and how can we build models that can help us do better planning. Secondly, we look at energy. And we talk about the power grid specifically and look at how the connected devices are going to interact and how to leverage intelligence to make better decisions. Third, we look at markets. We leverage the ideas from electricity markets, think about how to design a more equitable power grid and what that means. I'll talk about this in the talk. Now, let's go into weather. So weather data is used in many domains. You can think about many. Some researchers use it for agriculture to understand how temperatures impact crop yield. Some use it for healthcare to understand how extreme heat can impact people that have pre-existing conditions. Others, like me, use it for power grid studies to understand how the different components in the power grid will be impacted by temperatures. Now, how do utilities use weather data today? Typically, they take historical data, then they have temperature, humidity, load, forecast, renewable generation, and they put that into a power grid study, and then they make decisions for the next couple of years, sometimes 5 years, sometimes a decade. However, we believe that if we have more data points, so which means if we have more possible scenarios of weather, then we can have much more robust decision making, which is the fundamental thing that drove us to do this piece of work. And then also, if you think about the data type that we need, power system studies, you require fine resolution data because the systems that you're simulating, the dynamics happen at fine time scales. For example, you want to understand how the transformers would be impacted. You don't want one day temperature, you want the diurnal cycle because you want to capture the peaks. However, climate scientists really care about averages, so long-term, seasonal, decadal, how the climate is changing. And so we wanted to bridge this gap by developing a method that can help us provide stochastic weather data that can help us capture much more scenarios. This brings us to temperature GAN. Temperature GAN is a model we developed. Essentially what we do is we take in historical observations of temperature in different regions, and then we put that into a generative model, which I'll talk about in the next few slides. During sampling, we lock that out and then just sample from the GAN. We create the exact region we want, the time we want, and the number of samples we want. And we can produce many realizations of temperature. Now I'll talk about the model. So the model is a generative adversarial network, and I'll explain what that is. So you have a generator, which is what we're going to use to produce that data. And then we have two critics. So one essentially penalizes the spatial structure of the temperature field. And the second one penalizes the temporal structure, so how well it's capturing the diurnal cycles. Then those two critics get to see the data. The generator never sees the data. Then the generator during training produces samples. And then those samples essentially go into both of the spatial and the temporal critics. And then they combine it in a loss function. After that loss function is combined, it passes back to the generator. So the generator tries to learn without ever seeing the true data. Eventually, we train this over time and then compare this. Now I'll show some results. So here are videos of one example from the model. The left is the observed, the right is the generator. And you observe that the model is capturing the spatial pattern, but also capturing the temporal structure within the data set. I'll sip some water. Then I also showed the same similar results for a different region as well, Nevada, which has a distinct temperature profile. So you can perceive how well the model is behaving. Now, these videos look good, but how good? So we wanted to quantify this model, but quantify the performance of the model by proposing different evaluation metrics, which I'll explain. The first one was called Frichet daily mean temperature distance. And the idea is we wanted to measure how well, in a distributional sense, the model captures what's in the ground truth. And so for this one, we essentially compute the daily mean temperatures. And we assume that the bulk of the distribution of the temperatures follows a normal or a Gaussian. And then we can compute the distance of the parameters. So we capture the observed mean minus the generated mean, take the square distance, do the same thing for the generated and standard deviation. And the good thing about this is that the metric actually admits the same values, the same metrics as temperatures. So your errors are in temperature values. And then we show this result for a particular region, like Oregon, and we can see that the average distance is about 0.3, less than 1 degree Celsius. And this is quite good because if you look at all the months that we're generating, it's capturing the distinct distributions for each month as well. Now, I'll talk about the second metric. It's called spatial pixel-wise average correlation distance, or SPACE. And so I invented this metric, and how it works, I'll explain it with a picture. So imagine you have some samples. So I generate a sample, a 3x3 image, and each box is a pixel or temperature value. Then I unravel that sample essentially into a feature vector. So now this is a vector, and each piece is a temperature. Now I subtract the mean of all the examples, then I can compute something called a correlation matrix. It's essentially a normalized covariance. And then this matrix captures the spatial coherence or the structure of that sample. And so using this idea, we can then take the generated samples, that matrix, we can take the observed, its own matrix, then we can take the distance between that. And that gives us a value called space. And it's bounded, so maximum is 2, minimum is 0, and lower is better. And then we'll just show how the model behaves over time. And we observe that for both regions, in fact, for all regions, the model does learn to reduce the metric. However, it's not trained on that metric, so which means it's capturing spatial structure. Finally, I'll talk about quantile plots. However, I'm leading to something more interesting, but I wanted to explain what quantile plots mean first. So imagine you have a sample A. So imagine you can pick up a bunch of balls and they have different weights, and you order them according to their weights. And then you have sample B, you do the exact same thing. Now we implicitly assume that each of these sample A and B come from the same distribution. So which means that each of them are from kind of the same class. And also the sample you get is not dependent on the other sample. So each of them are independent. And then you essentially have an dual axis where one axis is sample A, one axis is sample B. Then you start to plot the values against each other. Now, when you plot the values against each other, after you can draw a line. Now, what does this line tell you? It essentially tells you the distribution similarity. So how close they are to the line means how similar they are distributionally. And so this is a visual cue that's commonly used in statistics. And so we extend it to something called a QQ envelope. Essentially, we generate multiple realizations. So we wanted to capture how the model behaves at different quantiles of the temperature values. So what you see is quite interesting, and I'll explain it. What you see now is that at the bulk of the distribution, the model is quite slim. So which means that essentially it's more certain about the distribution. And at the tails, you can see there's a wider envelope, which means also that the model is not overfitting. So which means that at the tails, you have fewer examples. So you should expect that the envelope should be wider. So I'll give the takeaways and contributions. One, we've introduced the generative model that's able to do operational planning because it can produce samples at fine spatiotemporal resolutions. Secondly, we've leveraged it for region and time-based sampling. Now we've shown that the models, the examples it produces are true to each region. And third, we've developed evaluation methods to actually evaluate this model properly. And finally, we've shown that this model produces an envelope over all the realizations you can possibly have, which helps you to have much more robust operational planning. Now that we've talked about weather, we can go into the energy system, and specifically we'll focus on the power grid and electric vehicles and how to integrate those together. So we have two main topics here. One is the electric vehicle load scenario generation. And the second one is grid integration and optimization. And you can imagine that the first one feeds into the second one. So why do we care about electric vehicles? Well, the adoption is accelerating. If you think about the amount of power you need to use to charge an electric vehicle, it's about the same power that 50 homes use at once. And so it's really important for us to be able to coordinate all these resources and leverage the flexibility that we might have so that we don't have to expensively overbuild. At the same time, if we can essentially capture the different types of charging or different types of EV charging, then it can help us plan better. Which brings us to something called EVGen. So EVGen is a machine learning model we use to learn EV charging loads. It also uses the generative adversarial network framework. And the key idea is it has a generator and a critic, similarly to what you saw before. And then the critic always observes the ground truth. The generator never observes the ground truth. And then you have some noise and a conditional variable. Now, the conditional variable specifically was to help us disentangle the different classes of charging. For example, fast charging versus slow charging, early charging versus midday charging, without exactly telling the model which one is which, because the data was unlabeled. And then we train the model similarly as before, generate samples, we have a loss, and then be trained. Now, what can we use this to do? We have EVGen, you can use to sample a type of charging, like early morning, midday, late afternoon. You can sample as many as you want, so you can run different types of scenarios. We compare this model to a Gaussian mixture model, which is the baseline, and we show that our model was able to capture the distinct modes better than the Gaussian mixture model because it makes fewer assumptions of the data distribution. Now that we've talked about EV load scenario generation, I'll go into the grid integration and optimization part. So the electric grid is truly a concept of many devices. It comprises many things, and it's honestly, the more I learn about it, the marvel how it works today. You think about the grids, we think about the integrating EVs into the grid, we need to have good modeling. We also need to have a detailed dynamics of different subsystems. So we built something called EV EcoSim, a multi-time scale co-simulation platform. And it comprises of different components, such as the battery, the solar transformers, and charging systems. Now, what we're thinking about when we did this, we're thinking about a few things. One, we wanted to understand the impact that EVs would have on the grid when they're plugged in. We also realized that different devices require different resolutions at which you should simulate them. And so it was important to have that flexibility to do multi-time scale simulation. And then finally, which was missing in the literature, was the asymmetry between the optimization problem you're solving and the true system. I wanted to be able to capture this cost that could be incurred when you make some assumptions on the model. Also, EV comprises of a few things. We can do cost analysis, so detailed levelized cost of energy, to understand which is the best system to build. We also do grid impact analysis, because at the end of the day, if your solution is not grid feasible, it's meaningless. So I'll talk about two main things. We did a lot of work on this, but I'll focus on just two main things. One is on the battery system identification module, and the second one is on the cost of the battery controller model fidelity on your system cost. Now, I'll introduce us to some types of battery models first. So the first type of battery model we'll talk about is bucket model. It's a simple model. It just treats the battery as a container of energy, doesn't capture any physics. The second model is an equivalent circuit model. It's a semi-empirical model that uses data to try to fit physical phenomena that actually exist in the battery. And the third one is a physics-based model. This is the simplest version, which is a single particle model. And it tries to capture the exact physics in the battery. So it models the electrodes and the diffusions. So the bucket model is commonly used in planning problems, optimization. Think about most papers you read about this topic uses the bucket model. In our model, in our system, we use the equivalent circuit model because we're able to capture much more detailed dynamics of the system. So an equivalent circuit model comprises of different parts. We use real laboratory data tested over a period of 23 months, and we're able to fit a model that does pretty well. And so it comprises of the pseudo open circuit voltage, which measures the no load voltage of the battery or the cell. And then we have the internal resistance, which measures, it's like the high frequency impedance. So it just measures the instantaneous voltage drop when you load the battery. And then you have these two components, which measure more of the transient dynamics. So it measures things like the charge transfer resistance and polarization resistance of the battery. So we learn these things through data, essentially. And now I'll talk about the method that we introduced called open circuit voltage correction. So open circuit voltage correction comprises of 3 steps. First is that we use the initially measured open circuit voltage, or OCV, to fit a model 1. After we do that, we then use that model to learn a bias correction function. And after doing that, we then fit a new model to improve our model, essentially. And we'll show how this works. And so we show a plot here. You can see the blue is the experimental data. And we can see that with the open circuit voltage correction, we're always able to improve the accuracy of the model. In fact, it improves it like 3 times. I also show the results for a couple of battery samples. So these are real battery samples. And we test the mean absolute percent error as well. And they're quite low. Now that we have a good battery model, we'll talk about a case study for how we use EV ecosystem for battery fast charging. For fast charging sites, sorry. So imagine you want to build an EV charging station and you already have solar existing in the site. And you want to figure out how much battery should I buy. In fact, this problem is so real that we have it today at Stanford. The project I'm working on with RAM, the 247 carbon-free electricity, where we actually have solar and we're trying to figure out the battery type. And so imagine you have all these parameters right now. You know the battery type, the chemistry, so we use the NMC. And we also have a fixed 700 kilowatt capacity. And the question is, what is the most optimal battery size with respect to economic cost, which means how much money you would make. And we run this problem for a couple of scenarios, and we wanted to look at how the stationary batteries model fidelity influences your decisions or your costs. So from left to right, you'll see different models and results, and you'll see them increasing in complexity. So in the left, you have the bucket model controller, and then the battery aging is a linear aging model. And what you see is these are the levelized cost of energy we have. The next is the bucket model, but now we have an equivalent circuit model with nonlinear aging. Now you can see that the cost of the battery goes down because the linear model overestimates the aging of the battery. And third, we have the linearized circuit model, which we developed. Essentially, it's us using the voltage response as a way to model the battery while keeping things linear. I won't go into details, but essentially, it's better than the bucket model. And we find that we're able to reduce the levelized cost of energy even more. And so you can imagine a 90% difference in your levelized cost of energy. And this is a key detail that is used to make planning decisions. So once you build a battery, you can't take it away. So it's important for us to capture the detailed models because they have the true cost. So now we've open sourced our model in ecosystem. It's on GitHub. We welcome contributors, whoever wants to contribute to the project. It's quite exciting. There's many more things you can do with it. Finally, I'll talk about the takeaways and contributions. First is that we introduced EVGen, so a generative model that can produce charging data. Secondly, we've introduced EV ecosystem, a co-simulation platform for EV infrastructure planning, and also looking at the grid impacts and cost analysis. Third, we also developed an open circuit voltage correction scheme that helps us model the batteries better. And finally, we've demonstrated that model fidelity can have a significant economic ramification when it comes to planning a site. And so it's important to understand how the uncertainty in your models impact your decision making. Wow. Now we've talked about energy. So we'll go into the third part, which focuses on markets. And this part is quite interesting to me because it's something I started a year ago. And it's really about thinking about how we leverage the ideas that exist today to do better things in the future. And so for this part, we'll split it into two sections. One is dynamic pricing. And the second part is resource allocation and coordination. And central to this entire piece is equity. Now, I'll go through a glossary so that I can make some definitions and explain things so that it's clear. What is equity? So here's a picture that I feel explains it very clearly. So equity is thinking about the outcomes, equality of outcomes versus equality, we just think about the incentives or I'll just say the incentives, for example. But here you can think of each stool is like an incentive, but the outcomes are not equal, right? They all can't see the gain. So the goal is thinking about what outcome do you want and what decisions do you make to get to that outcome. That's the difference between equality and equity. Now, how do we measure it in my work? I'll give a picture to explain that. So imagine you have 4 customers. So each person is a household or anybody within the community. And you know their incomes and you know how much they spend on energy. So now energy burden, which is what we define, is the fraction of income spent on energy. And so you can imagine that household 4 has a lower energy spent, but they have the worst energy burden. Why? Because they have such low income. And so how we measure equity is in 2 mathematical definitions. One is called the ratio of burdens. We look at the min versus the max burden, the least versus the most burden. So the higher it is, the better equity, the more equitable it is. And the worse it is, the lower the value is. Similarly, we use something called the Gini index. It's an index used in economics usually to measure wealth disparities. And so the worst value of a Gini index would be 1, and the best is 0. And so this is just a pairwise difference of energy burdens between all the customers or all the households. And so you also want to make this as high as possible because the higher it is, the more equitable the system is. And so this is the fundamental grounding of our work. And so I'll talk about something called locational marginal prices now, or LMPs. And how they work is that you have something called an independent system operator who's trying to make sure the grid doesn't break and we all have electricity. And then they ask the question, what is the minimum cost of operating this grid? And then after they do that, they obtain something called prices. They obtain prices everywhere, which tell you the cost of energy at each grid location. Now, these LMPs encode a few things. One is they encode the generation cost, which means how expensive it is to produce power. The second thing is the transmission congestion. How expensive is it to move power from one place to another? And finally, the last is line losses. How much are you wasting energy when you're moving it from one place to another? And really, I started to think about this in a way that these prices can be a signal of system design inequity. Now, I'll talk about time of use rates. Time of use rates is something that's common to most of us today. So most individual homes don't really see dynamic prices. They see time of use rates that are fixed over a long period. And the idea behind time of use rates is that utilities want to figure out which times in the days energy is most expensive and try to encode that in one fixed rate and then give that to consumers. So you can imagine when there's a lot of sunlight, energy is probably going to be cheaper. When there's less sunlight and there's more congestion, energy will be more expensive. So this is what time of use rate does. Now going to part 1, dynamic pricing. So what is dynamic pricing? So dynamic pricing is a way of pricing goods, anything, essentially, that captures the operating conditions of the system that you're working in. For example, we see dynamic pricing in our lives every day. The stock markets, anyone trades stocks here. You know, when you want to buy the stock, if that stock gets popular, for example, when GameStop had this wild dump and the price tanked after reporting because the supply went really high. So those are things like dynamic pricing. Also, like Uber and Lyft, I think this one was the most glaring to me. One day I was in the same location as a friend of mine, and I ordered an Uber to the same destination, and the prices were different. So Uber does dynamic pricing to maximize their profit somehow. I don't know how they do it. And then the third thing is street markets. So many of us are familiar. I'm from Nigeria, so And this is something I don't like about America, actually. You can't go to the streets and price them good. There's no dynamic pricing. You go there, in Nigeria, there's dynamic pricing. You go to the streets and they tell me, buy this for $50. I'm like, no, $20. Compare that price. So that is what dynamic pricing is, essentially. So now we introduce something called equitable dynamic electricity pricing. And the picture is simple. We have something called a power distribution authority, which is essentially algorithms we designed to produce prices that produce a desired outcome. And the two outcomes we want is that we can minimize voltage fluctuations and maximize price equity or parity within the grid. And how it works is, this is a flow chart. So essentially what we do first is we import the power system network parameters. Then we construct something called a Jacobian. You don't have to understand that, it's just how to describe the power system. And then the PDA updates the prices using two algorithms. One is called an implicitly constrained load method, and the other one is a gradient-based method. And then once the prices converge in this loop, we can then set the prices for the day. Afterwards, we then run an AC power flow simulation to see if our prices give the desired outcome. And then we measure the gradient impact. Now, we compared our dynamic method to time of use rates, and we found that we're able to essentially smoothen out the voltage profiles, the magnitudes, while still maintaining price parity. So here are the summary of the results. So we see that the green and gold is best. Star is our own algorithm and the values. So for equity, we're trying to achieve the value of 0. 0 is the best we could achieve. And the worst is minus infinity. And we can see that the values for our methods are quite small. So ICD is about minus 1.27 into the 6. So we see that our methods do perform better than time of use rates while also maintaining price equity. The second part I'll talk about, which is newer work, is called equitable resource allocation and coordination. To explain this, I'll talk about the framework that we propose. So say we have a distribution grid, have a substation, you're also able to capture weather. So how weather is impacting the grid. We have a low income node and a high income node. Now we populate this network with homes, EVs, all sorts of loads to make it rich and robust. Then we have some resources like battery, solar systems, or maybe even want to build new transformers or upgrade a transformer. And you allocate these resources somehow. Let's say we don't know how to do it, but we just do it. Then we solve an optimal power flow problem. What that gives us is the marginal price of electricity at each node. So you can imagine that each decision you make, so how you allocate resources, will influence the marginal prices as well. And then we measure equity and use it for decision support. So the key questions that we can answer with this is the following. How does the allocation of energy resources impact equity and energy burden when you start to consider the true grid conditions? How should we prioritize incentives so that people can adopt DERs or distributed energy resources? Are there unintended consequences that come up when we define the same concept in different ways, which I'll talk about a little bit. So a decision support framework that can capture all of these angles at which we look at equity is important so that we can make better decisions. We use our framework for a case study where we have two income nodes as described. They both have distinct income distribution. So one is the low income node and one is the high income node. And we're trying to figure out how do we share battery capacity. So say we have a fixed 80 megawatt or 80 kilowatt hours. Which region should get more of that? Is it the low income, should they get all of it or some of it? We can use this framework to answer that question. So first, we wanted to look at are decisions we make sensitive to how we define equity. So we show some results. So one is called the ratio of burdens, which I described earlier. And one is the Gini index, so the 1 minus Gini index. And now on the primary axis, the y-axis, you have the low income, so we can count capacity to the low income, versus the x-axis, which you have the high income. So as you move along the x-axis, you are increasing the battery capacity you give to the high income node, and you are reducing the battery capacity you give to the low income node. And then the colors, blue, the yellow is higher equity and blue is lower. So you can see how your decisions you're making is changing equity in terms of the system. So in this case, we see that both definitions don't really change. The outcomes, essentially, they're both telling us that this is the optimal, in terms of equity, this is the best resource allocation. Now, we also looked at group aggregation effects, because many times when we think about policies, they look at groups, policy along a zip code or a region or a country. So you kind of aggregate groups to make decisions. I wanted to understand how, when you aggregate a group and you go back to the individual level, are there any changes and what are those? That's important for making decisions. To understand the person that's going to be impacted the most vulnerable, they can get averaged out when you start to make averages. And so what we see is that there is a difference, a slight difference in this case, and in some cases it could be worse. And so really it's important to consider these. Also, you find that when you average people, the equity level you measure is upper bounded, essentially, is upper bounded by the nodal equity versus the individual equity. So which means that in averaging people, you can seem to achieve more equity than you probably can when you look at the individual level. Also, we notice seasonal differences because we're able to capture the impact of temperatures on the power systems by looking at the transformer aging. So we can look at the seasonal differences across as well. And we can find that, of course, there are seasonal differences in terms of equity as well. And so having policies that are not just static, but are seasonal can help improve the outcomes in terms of equity. Last, I'll talk about something called dynamic pricing, which we talked about before, but I'll talk about the impacts on equity. So this curve you're seeing here essentially is showing an iteration, and each iteration is a dynamic price you set. And at each point, you measure the system costs. And so what we see here is that if you do dynamic pricing, which means we're pricing the true condition of the grid and having users respond, we can reduce the system cost. And what we find is that we can also preserve the profits that utilities make. So essentially, we're just shifting prices in a way that makes the grid better. We're still retaining our average profits. So this, you can think of it as savings. What we see is that equity gets worse. So there is a trade-off between system efficiency and equity. Wow. What do we do? Maybe we can share the savings. So if we share the savings from dynamic pricing and share that with others, the people in the grid or the homeowners, and you share it in a way that's proportional to their incomes, then you can improve equity beyond the baseline, beyond the status quo. So the status quo is time of use rates, where we don't do any dynamic pricing, we just give everyone prices. And we can see that we can improve equity much better if we leverage the profit sharing from savings. And we see the same thing for a different metric as well. So this is the aggregated metric. We see that it also increases for the aggregated metric. However, there's one thing I wanted to point out, which is that the metrics actually do matter. So the left is the disaggregated individual equity. The right is the aggregated nodal equity. And what you see here is that the marginal improvements you get at each iteration is different. For example, the first one, it tells you that at the first iteration, you get a huge jump. And the second one, aggregated, tells you that you need to get to after the first iteration before you get that huge jump. And each of those iterations have a different savings. And so which means it tells you how much money you can share to improve equity. And so between the 0 and the first iteration, the savings was about $200. So which means you only have to share $200 to this to the community to improve equity. However, the second one is telling you that to really improve equity, it's more expensive. And so metrics do matter. So now I'll talk about the takeaways and contributions. So first, we've introduced a dynamic pricing algorithm that is also equitable, and it's better than the time of use rates when we run it on simulations. Second, we've introduced the comprehensive decision support framework to help us make better decisions, capturing the true conditions of the grid. Now, we've shown that though dynamic pricing can exacerbate equity, so it can make equity worse, we can make it better by using the savings from dynamic pricing. And so finally, I wanted to leave a note saying that comprehensive analysis that we use for grid planning decisions really require us to leverage all these computational tools because we can really model the world better. And so we want scientists, policymakers, people like me, I guess, to transition the grid and make it more equitable. Now I'm going to recap what we talked about today, and thank you so much for staying with me. So really this work has been a constellation of all my thoughts and my point of view over time. So first of all, we introduced something called temperature GAN, a generative weather model that can produce temperatures at fine spatiotemporal resolutions to help us do better operational planning. Secondly, we've talked about the grid, and we introduced two main things. One is EVGen, which is a generative model that can produce different charging types, like fast charging, slow charging, which then feeds into a grid model that we can simulate accurately to understand, first of all, one, the impacts of EVs on the grid, but also how to build and make better planning decisions that are good for the grid, but also economic. Finally, we've talked about markets, kind of leveraging the ideas from electricity wholesale markets to do something called dynamic pricing. And we show that dynamic pricing is always better than doing nothing. And in fact, we also show that dynamic pricing could make equity worse. However, the savings from dynamic pricing, if they share to customers, then we can improve equity beyond the base. Together, we built a comprehensive decision framework for transitioning the energy system to 24/7 carbon-free electricity, hopefully. Fingers crossed. Here are my picture credits, and I'll go into some acknowledgements. So I would like to acknowledge my funders over time. So Stanford Data Science Scholarship, the Chevron Energy Fellowship, then Bits and Watts as well, which was my first experience, honestly, here at Stanford, working with lots of people like Siobhan, Lily, and then Siemens as well, which I collaborated with, and I think funded us.